We continue with the idea of forces of evolution. These are factors that cause a population to be forced out of genetic equilibrium, out of a situation in which evolution is not occurring, and causes the population to change. Today's focus is on the idea that the Hardy-Weinberg principle said that in order for a population to stay the same, it must not have any natural selection. We're going to talk about three different versions of natural selection today. In other words, three different ways in which selection can cause a population to come out of genetic equilibrium. And one of those is the idea of directional selection. Now, before we can talk about that specific type, let's look at the graph for a second and focus in, please, on the dotted line. The dotted line represents a distribution of data, oftentimes referred to as a bell curve. You can see why it's called that, obvious reasons. And it's a pretty common distribution of data. Think, for instance, about human height. If we look at this extreme end here of our bell curve, we might think of this as tall people. There are people on Earth who are extremely tall, let's say 7 feet tall. But of course, there aren't many of those people. There is the other extreme as well. There are people on Earth who are very, very short, but again, not too many. Most of us fall somewhere in the middle of being an average height, and therefore the population is sort of swollen at that point. And so you have this distribution that is, as I said, the bell curve. Keep that in mind as we talk about different types of natural selection today, because it will continue to apply. Getting back now to the idea of specifically directional selection, you can see based on the definition, it is the type of natural selection in which one extreme form of a trait is eliminated while the other extreme is favored. An example here, as we've used in the past, would be that of giraffes. Giraffes at one point in time were not as tall as we know them to be today. The neck was not as long. That doesn't mean that all giraffes were the same. There was still a bell curve distribution. There were giraffes that were extremely short. There were giraffes that were the tallest of the population, but most giraffes fell somewhere in the middle. Of course, giraffes eat leaves, and as the leaves at the bottom of trees were eaten, who was at the greatest disadvantage? Well, the short giraffes were, because they didn't have access to food. So they would die off as a result of that disadvantage. As that happened, and individuals who were then perhaps average in height, or those that were tall and at the greatest advantage, were the ones that lived and therefore reproduced and therefore passed on their traits. And by eliminating the short ones and breeding with the tall ones, the average height of the giraffes over the course of many generations moved, in this case, towards the right, so that what used to be a short giraffe is gone. What used to be an average sized giraffe is now, relatively speaking, a short giraffe. What used to be a tall giraffe is now simply average. And some giraffes are even taller than the tallest used to be. That's the idea of directional selection. And it's a pretty common idea when it comes to evolution. Think about whales getting larger, cheetahs getting faster, human brains getting larger. All of those are examples of directional selection. One extreme is favored, and therefore the population over the course of generations moves in that one direction. Another version of these same events would be that of stabilizing selection, type of selection in which both extreme forms of a trait are eliminated while the average form of the trait is favored. Again, we go back to this idea of the bell curve. There in the dotted line is our bell curve. In the blue represents the new population, and what has changed over the course of many generations is that this extreme end of the bell curve, this extreme end of the population has been eliminated, but this other extreme also eliminated. For whatever reason, those extreme forms of the trait did not have an advantage in the population, And so they were eliminated, and the average, which apparently was advantageous, became even more and more prevalent. A natural example I can provide of this is that of human baby, and specifically human baby head size. When a baby is developing and it needs to develop fully and completely before birth, if it does not, if a baby has a very small head and is underdeveloped, it is pretty frequent over the course of the last few million years that that baby probably didn't survive. And so that one extreme end here would be eliminated from the population because they would never live and grow up and have babies of their own. But of course, there is the other extreme, the baby with a head that is large. Well, that's a problem when it comes to birth because the baby's head, which has to fit out of the birth canal, cannot. And so not only might that baby die, but the mother might die in childbirth as well. And so that sized baby would be eliminated as well. It is only the baby that has fully developed, but not gotten too large, that lives and therefore has the chance to grow up. And then when two average sized babies have a child together, then they too are probably going to produce another average sized baby. And so you can see the stabilizing selection that has occurred here with the average being advantageous and both extremes being disadvantageous. That's a natural example of selection, but there's also one I can provide that's an artificial one. Most of you are probably familiar with the dog breed known as Huskies. We tend to think of them as sled dogs, and they have been artificially bred in order to serve that function. There's a problem, of course, with sled dogs or Huskies that are too small. And we can look at this end of the bell curve to think about those small Huskies. They're too weak. They need to pull a sled, and Huskies that are small are not big and strong enough to do that. So they are eliminated from the breeding competition, the breeding that is artificially being selected for by the breeder. On the other hand, Huskies that are large, you might think, hey, that's good. The problem is that the Huskies have to run across the top of the snow, and Huskies that are too big will sink down in the snow and therefore also not be able to pull a sled. So there is a happy medium somewhere in between. Breeders want Huskies that are big enough to pull the sled, but not so big that they're going to fall down into the snow. So again, an example of a stabilized situation. That leaves us with a third type of selection that is known as disruptive selection. Type of selection in which selection favors both extremes of a trait and eliminates the average. One last time here, we go to our bell curve, and you can see the change in blue here of what has happened to this population. For some reason, this extreme end of the population has a trait that is advantageous to survival, but the other extreme also advantageous. Both extremes live, grow up, and reproduce. What seems to be at a disadvantage would be the average form of whatever trait we're talking about. And so it is being eliminated, or at the very least, drastically reduced. Both extremes survive, and the average is being eliminated.